Welcome, everybody. My name is Jennifer Griffith, and I work at NMOA, which is the Northeast Waste Management Officials Association. And I'm showing our website here so you can read for yourselves, too. We are an interstate association of the 6 New England states, New York and New Jersey. The waste programs work together. That's the solid waste and the hazardous waste, the toxic use reduction, the pollution prevention programs, and then also the waste site cleanup programs. So this webinar is sort of organized through the waste site cleanup programs. One of the priorities for the waste site cleanup program at NMOA is training of state staff. But then a lot of times we feel that, it's good that everybody's on the same page, and so our trainings are open to the public, which is what we're doing today. Another priority of our states has been PFAS for the last, I think, 5 years now. We've been doing a lot of information sharing and training on PFAS. So we're combining today the training priority and the PFAS priority. And we've got a great webinar with some distinguished experts this afternoon here in the Boston area. NMOA is located in Boston, so it is the afternoon for me. So part of the reason why I'm showing the NMOA website as well is because after the webinar, within a few days, it takes a little while, the presentation from today will be posted on the NMOA website. So this is just nmoa.org. Then you choose here in the left-hand nav the Waste Site Cleanup program. You get to Waste Site Cleanup, and we have events. And then upcoming events are at the top, and the one the furthest in the future is at the very top. These are a couple of conferences that were supposed to happen in 2020, and now they're in 2022. Hopefully they can happen then. But then also some upcoming webinars on PFAS that we have scheduled that you should probably already know about. And then here's past events. So if you just keep scrolling down, we have past events. Presentations from all these webinars are posted. So if you scroll down, obviously we do a lot with PFAS, but we've also done things that are not related to PFAS. We had a couple webinars on PCBs, a couple on vapor intrusion. These are some webinars that happened last summer. And then, even in our more distant past, we had actual in-person workshops. Those are on a variety of technical topics as well. So if you just keep scrolling, there's a lot of really good information on the NMOA website for the future. So with that, let's see. There's so many people on the webinar today that we will not be able to do questions, live. So you're going to have to type them in. You can type in questions at any point. That's, you don't have to wait until we have a break for questions or till the end. You can just type them in at any point, and then I will be monitoring those and ask them of the presenters. So I think that's the main logistical stuff. So now I will introduce our presenters for today. So make Liz the panelist. So we've got 2 presenters that are going to sort of present jointly today. We've got Dr. Nancy Rothman. She's the CEO and a principal scientist of New Environmental Horizons Incorporated and has over 30 years of experience in the development of methods, analysis, and data evaluation for organic compounds in the environment. She applies her depth of experience to evaluate usability of current and historical data, and in the development and review of project-specific quality assurance project plans for environmental investigations in support of NOAA's Natural Resource Damage Assessments, the U.S. EPA Superfund Program, the U.S. Army Corps of Engineers, and state-led programs. Dr. Rothman, she's located in New Jersey and is an appointed member of the New Jersey Department of Environmental Protection Science Advisory Board and serves on 2 ITRC teams that are developing technical guidance related to PFAS and 1,4-dioxane. So welcome, Nancy. Our other presenter today is Liz Denley. She is TRC's PFAS Group Program Director and also the Quality Assurance and Chemistry Director. As a project QA chemist at TRC. Liz is responsible for providing QA and quality control oversight in support of different environmental investigations, including remediation programs, ambient air monitoring, and human health and ecological risk assessments. She's currently serving on the ITRC's PFAS team and is co-leader on the PFAS naming convention sub-team, and she won the 2017 ITRC Industry Affiliates Award for her contributions. She currently works on many types of PFAS investigations with a specific focus on chemistry, sampling procedures, data interpretation, forensics, QA/QC, and analytical methodologies. So these women really know their stuff and are going to share their insights with us all today. So take it away, Liz and Nancy.
Thanks so much, Jennifer. We're really happy to be here, and as Jennifer pointed out, if you have questions, please don't hesitate to type them into the chat board, and we'll have time at the end of our presentation to answer all your questions. Okay, next, Liz. Today we would like you to come away from this webinar with an understanding about usability, the analytical methods that are used for PFAS analysis, sampling precautions, and some of the issues related to holding time, preservation, etc. Next. Why do we bother looking at data? You may say, listen, I sent my samples to a NELAC certified laboratory. That's all I need to do. But know that a laboratory can perform the method exactly as written and still you might have issues with the data because your matrix can be kind of complex and cause issues with potential biases in the data. So it's very important to evaluate the data because making a decision about what we do with PFAS is important and costly. Next, please. So data validation is a very prescriptive process where we go through and use specific guidelines and look at each sample, each quality control measure, and add qualifiers to the data. And we can do either a limited or a full validation. An assessment is where we review the data for the major quality indicators and judge whether or not the data are of sufficient quality for your project objectives. So in other words, can we use the data in our decision making? In general, qualifiers aren't added to the data during an assessment. Now, both of these, the validation and the assessment, have their place. Validation may be really appropriate for a new site using a new laboratory. But overall, even if you do validation, you're going to have to do also a component of usability because the validation does not necessarily put a qualifier on the data if the sensitivity isn't met. So you might have to look at the data anyway from a usability perspective. And so it's a good idea to use both validation and usability in evaluating PFAS data. Next. So what do? We first, when we're doing usability, we make sure that all the compounds that are requested were reported. And I call this the time to make the donuts part of an assessment. You're really just looking at compound names. I requested X number of compounds, and all those compounds are being reported. That's the first line in usability. Then we look at the sensitivity, meaning what are the reporting limits or quantitation limits that are reported for the samples, and do they meet the project requirements? And then finally, we look at all the quality control indicators in the data package and judge whether there is a potential limitation. Is there a high bias, a low bias? Are there some results that are so egregious that there may be rejections of data or you can't use the data at all? So these three elements combined can give you a really good idea about the usability of PFAS data. Next, Liz. So what do we ask when we're trying to prepare for doing work for PFAS? Next. Okay, so, we didn't know what we didn't know a long time ago, right? So we would go out in our Gore-Tex raincoats with our glass bottles and used our Teflon tubing to grab samples for PFAS analysis. And happily, we've learned an awful lot from the time when PFAS was first determined, so that now we have to develop plans that really are specific to PFAS, because there are really important considerations with respect to sampling and analysis. So we look at the site history. We understand then, based on a conceptual site model, we have specialty design plans for sampling and analysis. And then most importantly, we establish project action levels. And all that information goes into determining a quality assurance plan or a sampling and analysis plan, SAP. And it must be very specific to PFAS. You can't just use your SAP plan for a semi-volatile analysis or a volatile analysis and expect it to be adequate for PFAS sampling. Next. So why am I bothering with this? Well, he told me to do it. That's a good reason, but it may be a permanent requirement. But let's say that you're in the middle of a site and you're looking at forensics, and to the east of the site there is a airfield. To the north there's a municipal waste landfill, etc. And so if you're looking at source identification or doing forensic analysis, the needs for the program may be much different than if you're just trying to look at a waste characterization. Do I have a problem? And then on top of that, if I'm looking to see about the effectiveness of a remediation system, those needs might be even more different than others. So for example, if I'm looking at the nature and extent of a plume, let's say I'm at an AFFF site, I certainly want to make sure that the C4 and C5 PFAS compounds are being monitored for my program, because these will be on the leading edge of a plume, and you would prefer to see the C4 and C5s before the C8 PFAS compounds actually become a problem. So if you understand why you're collecting the samples, and then you build your SAP around those parameters, you're starting off on a good basis. Next, Liz. So we have a lot of field quality control options: field blanks, equipment blanks, field duplicates, MSMSDs, and cooler temperature blanks. And really, field blanks have, in my opinion, and I think in Liz's as well, has limited ability to help us understand what's going on. We know that the ambient air pathway for PFAS is a very important pathway, and we're getting more and more information on that. However, a field blank is a sample of analyte-free water that comes in a container from the laboratory, is brought to the field, and during the sampling of one area of the site, or one sample, the bottle is opened, and when the sampling is done for that sample, the container is then closed again. So there's a very limited amount of time that you would have exposure to the air. So usually, if you have something in the field blank, in that case, you have a really big problem. More important blank is the equipment blank. And maybe we all sort of think, well, I take this equipment out of the packaging, and I'll just go and clean it off a bit, and then I'll take my field blank, the equipment blank, excuse me, and then I'll go out to the field and I'll collect samples, And obviously that's not adequate, because equipment blank should be performed after sampling and after decontamination of the sampling equipment to verify that, in fact, the decontamination process is acceptable. And it may be for your particular program, one equipment blank per day, per matrix, per parameter is sufficient. However, based on your sampling design, you may have a very large sampling effort, and you might have a lot of teams out there, and you may say, you know what, I'm just going to be safe than sorry. I want to have one equipment blank per day, per field team, per parameter. And so that the frequency for equipment blank would be something you would consider as you're developing your SAP. Field duplicates should be taken at a location where there is some detected level of PFAS, because if you just take it where you don't think that there's any contamination, you will not get any information on possible sample heterogeneity and representativeness of the sample for PFAS. So the field duplicate should be taken at a place where there is some contamination, while the MSMSD should be taken at a location that is not too contaminated, because if it's highly contaminated and the laboratory gets the samples in, spikes them, and then when they analyze them, they end up having to dilute them because the samples are so contaminated, you end up paying for an MSMSD that has no information for your samples. So, and the cooler blank tells you about preservation of the sample during shipment. And all of these field parameters should be identified in your SAP. Next, Liz. And what we do is we evaluate the various parameters for, like say, the laboratory performance and the method blanks, and we're going to discuss these at length. LCS, laboratory control samples, etc. The field performance is equipment blanks, field duplicates, and in laboratory and in matrix problems, we look at extracted internal standards. This is a term that we're using in this presentation, and it's a term that's used in DOD and some of the newer methods to represent the labeled surrogates. So the extracted internal standards are added to the sample prior to extraction. And then the injection internal standards are secondary standards that are added just prior to the analysis. And then we look at all of these components and judge whether or not the performance was acceptable. And as the stars show, there are some parameters that are not normally discussed in a level 2 deliverable or a summary data package. And therefore, if you need to know about this information, you would need a level 4 data package. Next, Liz. So the reason that we look at all this is that all of these different parameters can have a cumulative effect on the overall usability of the data. So for sample-specific issues are related to, shown on the left-hand side, field duplicates or the extracted internal standards. These are done in each sample so that if indeed there's an issue, it's just related to that particular sample. However, there are also batch-specific quality control, as we've shown on the right-hand side, that can affect the entire group of samples that are being analyzed. And therefore, if indeed you have a level 2 deliverable, if the laboratory has found that there's an issue with the start components, like the calibrations, the injection internal standards, they should actually indicate an issue or explain the issue in their project narrative. But otherwise, we'll be discussing, and Liz and I will be talking about all of these different parameters, the field quality control going forward. Okay, next, Liz.
Great, thanks, Nancy. So Nancy just gave a great summary, of why we need to evaluate data, what we need to think about before sending in samples to the lab, some of the parameters that we're going to be evaluating, the reasons we collect field QC samples. So now we're going to get into some of the, really get into some of the PFAS specific issues. So we'll start with sampling. I know a lot of you have probably seen, a lot of information on this, but it is important to data usability. So PFAS sampling is different from other sampling events due to an increased potential for cross-contamination of our samples to occur. Because remember, we're looking at very low regulatory screening criteria down to the parts per trillion. So there's the potential to cross-contaminate our samples due to the ubiquitous nature of PFAS and the many different products that contain PFAS. So how do we sample for PFAS? So sampling for PFAS in groundwater, soil, and other matrices is typically performed using conventional sampling techniques, but with a few modifications. So there are things you are going to do differently when you're sampling for PFAS. So as I said, we know PFAS are ubiquitous potentially in a lot of different materials. PFAS have been used in the manufacturing of items that we personally use and in items that we use in environmental site investigations. And some of the typical sampling equipment we use may contain PFAS. So the modifications to the sampling methods are generally to prevent this potential cross-contamination of our samples. Again, we need to be able to trust this data. We're going down to part per trillion levels, so preventing cross-contamination becomes very critical. So we'll go through some of the unique requirements when sampling for PFAS, which can make things a little bit more challenging. I do have a picture here of the Michigan sampling guidance. I think it is one of the more comprehensive sampling guidances for PFAS out there. And you can see on the right, they have separate guidance for sampling of all different media. So it is a really good resource if you need one. So the next two slides will go over some common do's and don'ts when sampling for PFAS. I'm not going to read them all to you, but just will point out a few things. Hydra sleeves are a passive grab sampling technique, and if you want to use them for PFAS, you just need to ensure that the high density polyethylene hydra sleeves are used. And the reason that the high density polyethylene is preferred over the low density polyethylene is because that low density polyethylene actually absorbs PFAS more than the high density polyethylene. Some other things you need to avoid: Post-it notes, blue ice. We do want to keep the samples cold at less than 10 degrees, but you should just use double Ziploc style storage bags with wet ice. You want to avoid using waterproof field books and just kind of minimizing how many things you're touching. Wash your hands, wear powderless nitrile gloves, and make sure you change them before every sample is collected. And that's something you would do with any contaminant, not just PFAS. So the first row here is the big one. You've heard over and over, you need to avoid the use of Teflon or polytetrafluoroethylene during sampling. So that can be in the balers used, tubing that we use, pump parts, but note that sometimes we do want to use Teflon when sampling for volatiles and PAHs or other organics. So in those cases, you'd want to make sure you collect those PFAS samples first with the required materials prior to switching over to Teflon lined tubing, say, for other parameters if needed. You also want to make sure that you always keep the tubing, in the original container in which it was shipped to prevent any possible contamination. And you do need to use high density polyethylene containers for the samples. So no glass, because PFAS can also be absorbed to the glass, just like the low density polyethylene. And make sure you only open that container during collection and never set the lid down to avoid any potential contamination. And you can see some other things listed here that also on the do not use list. So Nancy did talk about field quality control samples, and they are super important for PFAS. I think probably more critical than ever for this group of contaminants, and definitely needed to evaluate the usability of any data set. So like Nancy said, because of all the potential cross-contamination, we're looking at PPT levels. The collection of equipment blanks is critical. Many times I will get asked if PFAS is possibly in a particular material used in the sampling process. You could collect an equipment blank from a specific item in question, or you can even send a section or piece of the equipment, if it's practical, to the lab for a more vigorous, leachate analysis, depending on the ultimate project objectives. Those could be, like pre-investigation equipment blanks. Remember that all the water that you use for the collection of these blanks must come from the laboratory and be certified PFAS free. If for some reason you have to use source water in the field for the blanks, just make sure you send a sample of that water also to the lab for analysis. And when you're deconning equipment, you can use the typical Alkanox, Liquinox, but again, that final water rinse really needs to come from the laboratory and be certified as PFAS free. So it is an extra expense that you might have to deal with when you are ordering bottles to get this extra water that you'll need. Also, I just want to mention something about carryover. Sometimes we talk a lot about carryover in the lab from after high concentration samples, but we have to be careful of carryover in the field too. So the decon procedure is really important, and if it's not done efficiently, you can see carryover on the equipment, because remember, we're looking at PPT levels. So I would recommend, if you know a sample is hot for PFAS, has high concentrations, you might want to add even a methanol rinse to your decon procedure. But ultimately, those equipment blanks are going to be the best demonstration that your decon is effective and that your equipment is not contributing PFAS to the sample. And you can see some other rules here about no pre-wrapped foods or snacks because there's potential PFAS in the wrappings. And one of the unique properties of PFAS we see is due to their surfactant properties is the partitioning of PFAS to the surface in wells, ponds, and reservoirs. So it's almost like an invisible sheen concept where you see PFAS accumulating at the air-water interface. So you may need to think about where in the water column you want to take your samples to be most representative. And I will touch on that in a minute. But all of these rules, play into the evaluation of data for PFAS. So yes, you have to sometimes think about how your clothes are laundered. The rules say no fabric softeners, no new clothing, no Tyvek, no waterproof clothing, which I guess could be a problem if you're sampling in the rain, and cotton is best. But I tell people overall, use common sense. Many of the materials that have precautions like the clothes and the moisturizers and the sunscreens and PPE are not going to be of concern as long as they don't come into contact with your sample or the sample container. I mean, safety does come first, and PPE does have to be worn by our staff if that's what's required. Okay, so quickly, TRC and Alpha Analytical. We did a study to actually look at the potential for PFAS in commonly used sampling materials and the potential for these materials to cross-contaminate our samples. So we wanted to determine how much PFAS and which PFAS were leaching off of different types of sampling materials. So just sharing a couple of important notes from this study. The first I would tell you is that if you're looking at groundwater data, you really want to make sure you understand when tubing like low density polyethylene, Teflon or Teflon line tubing or a baler line were stored in a well for an extended period of time. So there may definitely have been some leaching of PFAS occurring in those cases. So you will want to know if those wells were redeveloped, and sufficiently purged to remove any potential residual PFAS contamination, which could arise from those materials prior to sampling the well. And you may need to use data with caution in scenarios like this. But another useful benefit from the study was the determination of different types of PFAS that may be associated with a particular sample material. And this may be useful in cases where we might suspect equipment contamination. Knowing the types of PFAS that may leach off of a particular sampling material may also be helpful in the forensics evaluation of sample data. And there is a paper published on this in the remediation journal if you're interested. So in relation to sampling, I also want to discuss some other concerns which should be thought about before collecting samples, and also if you happen to be reviewing PFAS data. So these are not going to be obvious in a lab data package, but these relate to specific field sampling procedures. So first, when you're installing soil borings or monitoring wells, you should assume that the surface soil is contaminated with PFAS. And therefore, you want to make sure you remove that top 6 inches prior to installing the boring or the well. So it's really, really important to minimize PFAS at the surface from getting into the boring or well during the sampling. Remember, again, we're looking at PPT, part per trillion levels in groundwater, and the contamination at the surface could really impact that if it does get into the well. So make sure you understand how the sampler is dealing with that surface soil during installation of borings or wells. So second is the groundwater sampling method. So low flow sampling is preferred for PFAS sampling. As I mentioned earlier, one of the unique properties of PFAS we see is the partitioning of PFAS to the surface in wells, ponds, and reservoirs. So again, like an invisible sheen, you have PFAS accumulating at the air-water interface. So you want to think about where in the water column you want to take your sample to be most representative. For groundwater, we do recommend sampling in the middle of the screened interval. Also, balers should probably be avoided due to this potential for PFAS to accumulate at the air-water interface. If balers are used or they were used on historical data, I would just make sure that at least one well volume was purged just to remove that static surface condition. And we've also had success with hydrosleeves, like I mentioned earlier. We even did a comparison to low-flow groundwater sampling and saw really good reproducibility. For surface water samples, since PFAS can accumulate at the air-water interface, you need to understand where within the surface water body that sample should be collected to make sure that the sampler avoids the air-water interface. So the depth at which these surface water samples should be collected can vary depending on the type of water body and whether it's a flowing or stagnant water body. So for a lake or a pond that is more of a stagnant water body, we do recommend sampling 1 to 2 feet below the surface. And for a catch basin or shallow outfall, which is more of a flowing water body, we recommend 6 inches below the surface. So efficient and consistent homogenization procedures have to be performed on soil and sediment samples. This is really critical due to the small mass, which is typically about 5 grams that are used by our labs, and we want to be able to generate representative data. So we want to make sure we give them a homogeneous sample as best as we can. And the last one here is very important, and it's how we or how the lab is dealing with aqueous samples with elevated levels of particulates. And I'm going to get into this one a little bit more on the next slide. So don't try and read the text on this slide. The point here is that something many people are not aware of, which is a major inconsistency in the lab community on the handling of aqueous samples with particulates, so surface water, groundwater, or wastewater for Pfas analysis. So all the text you see here are really just excerpts from different laboratory narratives on how they've dealt with these types of samples. So you do want to understand the level of total suspended solids in your aqueous samples. It's important for fate and transport and also treatment considerations. So those solids, those particulates, accumulate high concentrations of Pfas. And specifically, they'll accumulate some of the longer chain Pfas. And when those solids settle out in the water samples, concentrations can decrease by an order of magnitude. So as I said, the main problem right now is how our labs are dealing with these solids, and it is all over the place. So some labs will centrifuge or decant the samples and separate out the particulates and extract that remaining water sample. Some labs will take the remaining particulates, they'll do a separate extraction on it and then combine it with the water sample extraction. So you're actually getting a total result of what was in that sample. So there's no consistent method. And again, those solids can significantly affect Pfas concentrations. And not only the concentrations, but also the Pfas signatures that we create. So the example here on the right gives an example of a groundwater sample. It was sampled from a temporary well on the top compared to the same groundwater sample on the bottom from a 2-inch well that was properly developed. So the top one was the more turbid water. It had a much different composition than the clearer water. You can see higher concentrations of the 6-carbon perfluorohexane sulfonic acid and the 8-carbon PFOA. And we know the longer chain PFAS, and even more so for the perfluorosulfonic acids, adhere more to the solids. And sometimes the only way to even know the lab had issues with solids in the samples is to look at their preparation logs, which are not in the standard data package. I am finding that labs do not always include these details in narratives or the standard data package, and this information could be very important in how you interpret your data. So there is evidence that PFAS can adsorb to glass fiber filters. So if you did use them, you wouldn't know if a reduction in concentration was due to soil particles or due to adsorption on the filter. So as I mentioned, low flow groundwater sampling is the better option for groundwater samples to try to avoid any of these particulates. Some labs, again, will do that centrifuge step to separate them out. That's preferred over filtering. But there are tests being done now, I know, on various filter media, but it's definitely known that the glass fiber filters will absorb PFAS and should be avoided. And I always like to throw this slide in for any data usability presentation. Just remember, regardless if we're collecting soil samples for PFAS or another contaminant, just keep in the back of your mind that we are collecting samples that need to be representative of our site. So if we're not collecting the samples properly, the quality of the data is moot. And many times, a higher percentage of data uncertainty can be due to sampling activities. And also keep in mind for soil samples, for example, we're submitting a 4 8-ounce jar of sample that's representative of a certain location. And then our labs are subsampling that. They're taking a really small portion of that for their analyses. As low as 1 gram for metals, which we're not talking about today, but it could be between 1 and 5 grams for PFAS. So the importance of collecting samples at the right location and the homogenization of samples really can't be overstated enough. I'm going to turn it over to Nancy.
Thanks, Liz. So, I learned that I better not bring my Doritos out to the field to collect a sample. But every time we do this presentation, there's more and more information about the precautions that have to be taken, and that's so important. And another reason why it's so important to have a SAP that really is specific to PFAS. Here is a list of methods. The first method that we became available was EPA 537 version 1.1 at the top. It came out in 2009. This is not an isotope dilution method, and it had a limited number of compounds, 14 compounds, and it was for drinking water. In 2020 version, it's in between 2009 and 2020, there was an increasing need in the environmental community for PFAS analysis, and what ended up happening was that laboratories ended up performing what they called EPA 537 modified, which is shown at the bottom. And the big problem with that is that each lab performed their own modifications, and that no two labs necessarily have the same modifications. So we have a wide variety of data that was performed by various laboratories based loosely on 537, but adjusted and modified to be able to handle different matrices. In 2020, method 537.1 was issued, and this is an isotope dilution technique for drinking water, and it has an expanded list. In this table, really great resources are the Department of Defense Quality System Manual at 5.1, 5.2, 5.3 at the bottom. DoD does not have a prescriptive method, but rather there's a table B15 in each of these QSMs that contain performance-based criteria that must be used to generate data for DoD for matrices other than drinking waters. And so you may be familiar with the Compendium of Analytical Methods, CAM, or RCP in Connecticut, or the DKQP protocols in New Jersey. These tables indicate the quality indicator, for example, the method blank, the criteria for acceptance of that method blank, and then corrective action procedures. I found that the QSM table B15 been a really good resource when I've been evaluating all these laboratory EPA modified 537s, trying to establish whether or not the modifications were acceptable or not. Next, Liz. Okay, so here is just the tip of the iceberg. We know that every day we look in the literature, we find that there are new compounds that are being found, and currently this is what the number of compounds that are not routinely, but can be analyzed by analytical labs that we've seen data for. So these are the donuts, as I said, time to make the donuts. If you were to say to a laboratory, without having a SAP, I want you to run this sample by method 537.1, and then you had to report the data to NISDEC, you'd find that you probably would have made a mistake because there were compounds on the New York State DEC list that are not in 537.1. So it's very important to ensure that you understand what compounds you need to report for your data and why you need to report them so that you can make sure that you get the data you need. You have to communicate this with the lab, so work back and forth with the laboratory. Don't work in a vacuum. They can help you. Next, Liz. So this is just to start the process of understanding how PFAS is actually analyzed. This shows the extraction of an aqueous sample for PFAS. So you would send your sample, shown in the 250 ml sample bottle. Before the laboratory begins the extraction, they would inject into that sample the extracted internal standards, or the labeled surrogates, and then they would transfer the contents of that bottle to the SPE cartridge, and then rinse the bottle. This is what they should do: rinse the bottle with methanol and add that to the cartridge, and then through a series of washing, they remove interferences from the sample and then finally elute the sample. Now, it's going to be very difficult for you to understand whether the laboratory has followed this kind of procedure. And as you can see, there are some precautions. You know, there had been times when early on laboratories took an aliquot of the sample, you know, old data, or didn't rinse the bottle. If the bottle is not rinsed, it's possible that heavier carbon, you know, greater than 8 carbons can stick to the walls of the container. So without the rinsing, you may have a low bias in your results. And there's some other factors here that we're showing that can be an issue. So what do you do? How do you know that the laboratory is doing this properly? Well, you can ask them for their SOP and look for these buzzwords of entire sample or rinsing, or you can call them up and ask specifically if they do follow this. Next slide. So before analysis, the laboratory injects the sample with the injection internal standards and then introduces the sample into the LC-MS. The LC acts just like a GC does and separates out the components of concern, and the length of time from the introduction of the sample into the LC to when the peak comes out on the chromatogram, and the LC chromatogram is called the retention time. And generally, the higher carbon number comes out later than a lower carbon number. And also, there's an effect of polarity, so that if you see the peak that's all the way to the far right, the PFOA peak, the straight chain isomer is the large peak on the right, and the little hump to the left are the branched isomers because they have a different polarity than the linear isomers. So what we first do in investigating a compound is we look at the retention time, and we judge that retention time versus the retention time from authentic standards that were analyzed prior to the analysis of the sample. So this is not a theoretical retention time. It is different from one lab to another and different conditions from one instrument to another. So the retention time that's used is one that's laboratory specific. Next, Liz. The compound emerges from the LC and enters into the first mass spectrometer, at which point this compound is ionized into what are called the precursor or parent ion. So in the case of Pfas, the ion of the precursor ion of the parent is 499. That ion is then focused into the next mass spectrometer, and a secondary ionization occurs. And for Pfas, we have actually what are called 2 transitions that we're looking at here in this slide. The first transition from 499 to 80 is called the primary transition, and this secondary transition is from 499 to 99. This means that 80 is the quantitation mass that we're going to be looking at for Pfas, and 99 is the conformation ion for Pfas, based upon these 2 masses being formed from the ionization of mass 499. Okay, Liz? So when we're looking at whether or not we have an acceptable qualitative evaluation of a sample, first we look at the retention time. If the retention time for a peak matches the retention time from a standard, and we say, okay, I think maybe this might be the compound of concern. Then we look at the transition ions, and we make sure that, for example, for Pfas, that we have both mass 80 and 99 that come at about the same time. They also have to meet a retention time criteria, and that they're both present. So we need both ions to be present in order to have a positive identification. And on top of that, we have what is known as the ion ratio, which is the ratio of the amount of 499 to 80 to 499 to 99, those 2 transitions. And there is a theoretical ratio. That ratio can also be developed by the laboratory running their initial calibrations. Now, method 537, the drinking water method that was the original drinking water method, didn't discuss secondary ion transitions. And you won't find it in older data. And this will not probably be discussed in a level 2 data package either. But today, for example, the DoD requires secondary ion be monitored and ion ratios be evaluated, as does New York State DEC in their latest document. Or it started in October 2020, also talked about ion ratios. So if you have a compound or a sample that the ion ratios don't fall within the limits, does that mean that you don't have the compound of concern? Well, not necessarily. It may mean that there's an interference present that's causing one of the ions to be enhanced, and we're going to show a picture of that later. Or you can have a suppression of a signal. So in these cases, it would mean that we have to look at the data and say, well, there might be a limitation. I have to use this result with a little bit of caution. Maybe I have to look at other samples that were collected in the area to see if that interference may have been not be present, to make a judgment about what to do. Now, for some compounds, there isn't a conformation or the secondary transition, and for these compounds, we really can only use the retention time as the method for qualitative event identification. Next, Liz. Oh, mea culpa. What a mess. We have this miasma of detection limits, and in fact, the detection limits are very, very important. Liz. Next. So we have all these acronyms, and you can read all this. I'm not going to go into great detail, but for this presentation, I want to just point out that the RL, QL, and LOQ, in other words, the reporting limit, quantitation limit, and the limit of quantitation are going to be considered to be equivalent. And these are not necessarily the definitions that are being used by the Department of Defense. The DoD has very specific procedures for developing the limit of detection, the LOD and the LOQ, and I don't want that to be confused in this presentation. Okay, next, Liz. So here's a really simplified approach to what happens during calibrations. We analyze 5 or more concentrations of one compound. So this is showing just a single compound. And the relationship of concentration to response gives us the calibration curve. The region below the curve, as well as above this curve, are regions of uncertainty, because we don't know whether the compound is going to act in a linear fashion when we're not in the calibration range. And this region of uncertainty is where the MDL and IDL reside. The QL, RL, and LOQ ideally is at or above, they are at, sorry, I've learned to speak English, are at or above the lowest concentration standard that's analyzed in the calibration. Now this is the limit of my drawing capability, but these bars on that show the dotted lines, this is the wiggle room that's allowed for calibration, so that if we analyze a mid-level standard during calibration verification, if the response falls within the dotted lines, then we consider the calibration verification to be acceptable, and we can analyze samples. And I think for most part, this wiggle room is what causes the variation in LCS acceptance limits and surrogate recoveries and extracted ion recoveries is a calibration error that's allowable. And so when we analyze a sample, we get the response of the compound, and then through the magic of extrapolation, we can figure out the concentration of the compound. Next. So what is the takeaway from this? We really want you to leave here feeling, listen, if I make sure that I have my reporting limit, the RL, QL, LOQ is being reported, and that it meets the project action levels for my project, then I know that I have accurate data that's precise. I can use this to judge whether I'm below a cleanup standard and my action levels are exceeded or not, and I can use this in a risk assessment. These other measures of detection limit are not as accurate, nor can they all be used in judging whether you have an issue with cleanup. And so you have to be very careful about, using different detection limits, and really sticking to the RL, QL, or LOQ, which is equivalent or higher than the lowest concentration standard for calibration, will really serve you well. Next. So when you get a data package, first thing you do is you count the donuts. You make sure that the number of compounds, and I'm not kidding you how many times I found problems with this, the compounds that you want are actually being reported and that the right names are being used, and then you look and see what the reporting limit is. And this is the same as the LOQ, QL, and you judge, well, okay, I asked that the sensitivity be at a certain level. I want to meet some standard. Is that number below the standard? So the way that this should be read, for example, for PFBA, when it says not ND, it's non-detect. That means that PFBA was not detected at a concentration at or above 1.3 micrograms per kilogram. So if you have a problem with this, you call the laboratory and say, I don't understand exactly what is the sensitivity, what are the reporting limits, and what is how do I look at the non-detects? Okay, Liz, next. Okay, what should we use with PFAS? Most reliably, you can keep going, Liz. We should use the RLs and LOQs. We've talked about that a lot. They should define the sensitivity. And most lab sense can get 2 to 10 nanograms per liter. That's a parts per trillion for waters, and 1 to 5 micrograms per kilogram for soils, which is not going to be good enough if the laboratory is working under needs to be meeting unrestricted guidance in New York State, which has PFOA and PFAS at less than 1 microgram per kilogram is the project action limit. So you have to tell the laboratory what your project action limits to ensure that they can meet these. Do not use MDLs. Method detection limits, don't use them for non-detect values. The MDLs are statistically derived numbers that the laboratory generates once a year and does some frequency of evaluation to make sure that they're still valid, but they are not accurate. Now, J data should be used carefully. Here are 3 pictures that we have. The first picture shows, these are all in the same data package. The first picture shows a sample that PFBA was reported at 0.35 J nanograms per liter, meaning J means it's below the RL, but it was detected. The next picture shows a similar sample, but this was reported it was non-detect at 2 nanograms per liter. And then to the far right shows a sample that did have a good detect above the reporting limit, and you can see that the spectra is nice and clean. Next. So when we are looking at quality, we look at preservation and handling, we look at holding times for the analytical batch, and all the quality control for the analytical batch. The laboratories and the methods all indicate that a method blanket and LCS must be performed. You don't have to tell the laboratory to do that. However, if you want a matrix spike duplicate, you have to provide the laboratory with sufficient sample to do that analysis, and you have to pay for that analysis as well. They're counted as separate field samples. The extracted internal standards are added to all samples prior to extraction, and then prior to the analysis in the LC, the injection internal standards are added. So we look at all this kind of quality control as well as other factors to judge whether or not we have an issue with the quality. Next. So there are a lot of resources. One thing to point out that the field collection, as Liz so beautifully explained, really plays a part in the overall quality for PFAS. So you need to be able to evaluate what's happening from the field with the analytical data to determine whether there's uncertainty. And there's an overall impact of quality. You can't just look at one element and say, well, I think I've got a high bias, when in fact, if you don't look at all of it together, you may be misjudging the overall quality. So the guidelines that we show down below here are a few guidelines that you can use to judge quality. The New York State DEC guidance that came out in January 2021 has very nice tables for evaluation for data assessment of PFAS. And as I said before, the QSN 5.3 from DOD is also a very good document. The method 537 data validation guidance is fairly old, so it has limited usability. So now I'm going to turn it over to Liz to speak about some other aspects of quality.
Okay, so now we're going to look at some of the details of these laboratory QC parameters, and we'll start with something that's usually pretty easy, holding times. So almost all labs utilize the same holding times for solid and aqueous matrices, which is similar to EPA method 537, so 14 days to extraction, 28 days from extraction to analysis. Although you can see EPA method 533 has a slightly longer holding time for extraction. And from what I hear through the grapevine, that might be what the newest PFAS method that's coming out might have a similar holding time. So you're going to know the date that your samples were collected. Your labs are going to be telling you the date the samples were prepared, the date the samples were analyzed, and you want to make sure that you check that the holding times were met for each sample. So for most analytical parameters, when holding times are missed, the results may be potentially bias low. But for PFAS, it's a little different. So when holding times are missed for PFAS, there could be a potential low and high bias. And here is why. So it's going to depend on whether you're looking at perfluoroalkyl acids, the PFAAs, or the polyfluoroalkyl precursors. So for the perfluoroalkyl acids, which includes the PFAS that we hear most about, like PFOA and PFOS, these compounds are the ones that are persistent in the environment, and they're not going to degrade due to a missed holding time. However, the polyfluoroalkyl precursors, which include some of the replacement PFAS we hear about, like the fluorotelmer sulfonates, are not as persistent and they can break down. And so when these polyfluoroalkyl precursors break down, they actually form the perfluoroalkyl acids, the persistent compounds. So we could see a low bias with the polyfluoroalkyl precursors, which could break down over an extended holding time. And then this would result in a potential high bias for some of the perfluoroalkyl acids, which are the resulting breakdown compounds from the transformation of these polyfluoroalkyl precursors. So results for blanks are going to be in your typical lab report, and we all know the purposes of the blanks is to check for contamination in various steps of the process. So you do want to make sure that the lab reported a method blank for each preparation batch. So for every day of preparation, there's going to be a method blank. And typically method blanks are performed at a frequency of 1 per 20 samples. So if you have more than 20 samples in your report prepared on the same day, you're probably going to be looking for 2 method blanks. So we need to evaluate the method blank, the field blank, equipment blank results, and we want to know if anything is detected in these blanks and at what concentration. And then we're going to compare the results of the blank to the associated samples. So remember that the results of the method blank will affect the entire batch of samples that were prepared with that method blank. The results of a field blank would typically affect the samples collected on the same day, and the results of the equipment blank will typically affect samples collected with the same equipment. So there are some general rules of thumb to use, but basically, if the concentration in the sample is less than 10 times the blank concentration, then the result in the sample is potentially a false positive. Now, this rule of thumb may be different under different regulatory validation guidelines, but it's a common rule to use. This is the rule that's in the data validation guidelines for EPA method 537, and also it's also in NISDEX rules as well. So it's a pretty easy evaluation. Note that if a dilution was performed, you'd need to take that dilution factor into account when you're comparing the method blank results to the samples. But here's an example, where PFOS was detected in the blank at 2 nanograms per liter. So you would compare the sample concentrations to 10 times the blank concentration, or 20 nanograms per liter. So the first sample, 120 nanograms per liter, is above 20 nanograms per liter, so it's most likely a real detection. The second sample is 8 nanograms per liter, below 10 times the blank, so therefore it's most likely a false positive result. So the exact method of quantifying concentrations can differ between labs, and there's 3 general types of quantification. There's external standard, internal standard, and isotope dilution. But when you see a lab performing EPA 537 modified, most of us as data users are receiving data using isotope dilution quantitation. And the DoD Quality Systems Manual actually requires isotope dilution. So I think it's important to always take a minute to make sure everybody understands what isotope dilution is. You probably hear the term a lot, but you should know why it's so important. And isotope dilution is really the most accurate quantitation method. It's what we also use for dioxin furans, and sometimes we also use it for 1,4-dioxane. So how it works is our samples are spiked with a known amount of isotopes or extraction internal standards, also called label surrogates, prior to the start of preparation. So these extracted internal standards are going through the entire preparation and analytical process as the samples. And these extracted internal standards are the same as each of the PFAS being analyzed, and therefore they're representative of how that particular PFAS compound is going to behave in the matrix. So for example, here, the carbon-labeled perfluorobutanoic acid is associated with the perfluorobutanoic acid compound. The carbon-labeled PFAS is associated with PFAS. And there's a couple of instances, where one extracted internal standard may represent more than one PFAS compound because there just might not be an isotopic standard available. But in those cases, the laboratories will typically use like a closely matching extraction internal standard for quantitation. So the instrument is going to be calibrated for both the target PFAS compound and the extraction internal standard. So when the sample is analyzed, the concentrations of the target PFAS compound and the extracted internal standard are calculated. But the area of that extracted internal standard is used in the calculation of the target PFAS compound. So if the actual concentration of the extracted internal standard is above or below the true value, that will be reflected in this area count, and then the associated target PFAS compound would be proportionately corrected by that amount. So this allows the analysis to really account for any preparation or analytical errors, and really, most importantly, for any matrix interferences. These samples have different chemical, physical properties. They may have more going on than just the presence of PFAS. So these other properties might alter the response of the instrument and interfere with the identification or quantification of PFAS, and isotope dilution corrects for this. So note that the EPA method 537 does not use isotope dilution. DoD Quality Systems Manual again requires it, and most labs are utilizing this technique. So it's really the gold standard. If your lab's not utilizing it, you're not getting results corrected for matrix effects. It's probably okay that it's not used in EPA method 537, since that's specifically for drinking water samples. And we really don't have too many matrix interferences usually with drinking water samples. But once you start analyzing other media, you really need to use isotope dilution. I know that the state of New Hampshire, they recommend the use of it. I don't think any of the other New England states specify one way or another if it's required. I do know New York, California, and Wisconsin do require isotope dilution. So the extracted internal standards are going to be reported in your typical level 2 data package, and therefore they're going to be available for you to evaluate with any data set. So, how can isotope dilution vary between labs? So the first thing is, when is the lab adding the extracted internal standard to the sample? And Nancy talked about this, but we want the lab to add these standards to the bottle, so it's following the whole procedure with the sample. And you also want to ask your lab how long they're letting that extracted internal standard equilibrate with the sample prior to beginning that extraction procedure, because that can also affect the recoveries of these standards and ultimately of the target PFAS compound. So the labs are going to report the percent recoveries of these extracted internal standards, as you saw on the previous slide. And in essence, your result is being corrected for these percent recoveries. But although your result is corrected for the recovery, there are limits to how low or how high we consider acceptable. And guess what? It does vary depending on the lab or maybe even the regulatory authority. So what does it mean for you when you're looking at data? So if the percent recovery is greater or equal to 10%, it's probably okay. As the result for the affected PFAS compound, again, is going to be corrected for that recovery. When we start getting below 10% recovery, that could be considered more of a pronounced negative matrix bias. There may be some more effect on the data. So recoveries less than 10% may result, in some false negatives. And you can see here, if it's less than 10%, we may have potential low bias for the affected target PFAS, and we may actually even have to consider rejecting non-detect results if the recovery is less than 10%. And know that if the extracted internal standard recovery is low, it's only going to affect that associated PFAS compound. So if the carbon labeled perfluorobutane sulfonic acid is low, that's only going to affect perfluorobutane sulfonic acid, not the other PFAS compounds. Okay, so EPA issued a technical advisory on EPA method 537 back in 2016, and they had discovered that labs were treating linear and branched isomers of the perfluoroalkyl acids differently during quantitation. So this technical advisory specifically covers PFOA. The method, EPA method 537, had already covered the issue for these other compounds that listed here in the second bullet. But before this advisory came out, some labs were integrating the linear isomer only, some were integrating both the linear and the branched isomers, and that would definitely cause a potential difference in results. So prior to 2016, if you have historical data may be underreported by as much as 30% for PFOA. But linear and branched isomer integration has to be done manually by the lab, so it's important we know that our labs are doing this properly. PFOS, for example, is 70% linear, 30% branched, so not including the branched isomers could result in a significantly lower concentration. So make sure understand how the lab's dealing with this issue. I think now most labs have this under control. There are some uncertainties from lab to lab, knowing one, did they do it properly? Also, the interpretation of branched isomers can vary between labs. It may even vary between analysts because these peaks to the side here, which are the branched isomers, sometimes they're less defined than they are right here in this example relative to this single pronounced peak. So how an analyst or a laboratory may interpret that may vary. All right, Nancy, it's all yours.
Yeah, thanks, Liz. So I'm going to go through this quickly because we do have a forensics component too that is really going to be of interest. But here's an example of where I talked about the isotopes, the secondary ions come into play of deciding whether I have a problem or not. This data is from SGS Access, and they found by just using the one transition, the primary transition, 499 to 80, they found that PFAS was being reported as a false positive up to 220 nanograms per gram in egg samples. However, because they were doing their work and they were looking at the secondary transition, they realized it wasn't PFAS, and more work on their part showed that, in fact, the bile acids had a transition that were similar to the PFAS primary transition. So in looking at the secondary transition, they were able to verify that, in fact, PFAS was not present. So it's very important that if you've got complex matrices, and we're getting into more and more complex matrices, we're not just doing drinking water anymore, that these things like secondary ions and a real method development should be done on certain matrices. Next. So what are laboratory control samples? These are blank matrices like a analyte-free water or a diatomaceous earth or a sodium sulfate that's clean, that are spiked with the compounds of concern. All the compounds, all the donuts go into this. And then the laboratory prepares that LCS along with the entire analytical batch, which includes the method blank and your samples for up to 20 field samples. Next. And what you do is you make sure that the donuts are all there, and then you judge whether or not they're within acceptance criteria, and the laboratory should show your acceptance criteria. And you have to be careful that the range of acceptance criteria isn't too low, because as this slide shows, if indeed we have less than 10% recovery of an LCS sample, the likelihood that you could recover it from your sample would be very low. And it may be that you have, if you have non-detects in your samples, it may be a false negative. So we judge the LCS across the entire batch. So all the samples in that batch, if the LCS is low, all the batch is affected. If it's high, only the detects are affected. Next. Matrix spike is exactly the same thing. Spike in all the compounds of concern into a field matrix that you have provided. You've provided a secondary sample. And what we do is the same thing that we did with the LCS. Next, Liz. We judge the accuracy. We make sure we've got all the compounds, but we also have a precision component, which can tell us something about the heterogeneity of the matrix. If the RPD is very high, it could be an indication that the sample has hot spots and it's a very complex matrix. So again, if the recovery is less than 10%, it's possible that the unspiked sample, so for the MS-MSD, we only really take action, or not action, but we only feel that the unspiked or native sample is affected. But if it's less than 10% recovery, it's possible that you have a false negative, and you have to reconcile that you could have a data gap. Next. So overall, we summarize the quality looking at it, the blanks for bias, high bias, holding times. And as Liz showed, can have high or low bias depending on the compound. The LCS affects the entire batch, whereas the extracted internal standards and the matrix spike only affect the specific compounds and the specific samples that were used or evaluated. And then the subsampling, whether we rinse a bottle or we only take a subsample, can also affect the quality. Next, Liz. So when we're data comparability, this is a big thing for me, because I find that this is a factor that most people have the hardest time with, the fact that they're trying to combine data sets and don't understand why one data set is disparate from the other. So certainly there are the field collection techniques. A long time ago, we didn't know what we didn't know. And today you have different techniques. So when you're looking at data sets, make sure that you look at the field component. Handling at the laboratory, and Liz showed this. How did they handle the suspended solids in a turbid sample? Was there a problem potentially in old data where one laboratory is handling of a sample versus another? Not having equipment blank information or method blank information for historical data could mean that you have false positives, high bias in historical data that you're not aware of. Big one is not using isotope dilution for recovery correction. Old data, especially data that was used a modified 537 but did not use isotope dilution, was not recovery corrected, and therefore if you're comparing a recovery corrected data to non-recovery corrected data, you have that potential for a bias in the results. Degradation of precursors for various sites is really very important. You may sit back and say, well, listen, I never had a problem with any of these compounds, and all of a sudden I'm starting to see these Pfas compounds. What's going on? Well, perhaps you went to the site and started to do this great oxidative technique to get rid of chlorinated solvents. Well, oxidation processes can cause degradation of precursors, and if you hadn't been evaluating your site for the potential of having precursors present, it may be that your actions of remediation are causing compounds of concern to be emerging, or even just over time, the degradation of precursors can happen. Not including branched isomers, Liz spoke about that. Calibration differences can affect it. Sensitivity is a very important issue. You have to be looking at what was the value of the non-detect between data sets. You say, I didn't have any Pfas present, therefore, what happened now? They say it's detected. Well, make sure that you're looking at apples and apples for that. And then when it comes to compound name differences, this sounds pretty trivial, but it's not. Often laboratories had been reporting carboxylic acids, ex-carboxylic acids, but the sulfonic acids are reported as sulfonates. So if you're comparing data sets, you want to make sure that the names of the compounds are the same, and that if you're comparing it to a regulatory guidance, you make sure that you're comparing the correct name to the correct compounds. So Liz, back to you.
Great, thanks. Okay, so we're just going to switch gears a little bit just to have a very short preview on how you can use this Pfas data in forensics. We've just looked at some of the potential data interpretation issues associated with Pfas, And now I wanted to spend a very quick amount of time on how we can use PFAS data further for forensics interpretations, once obviously that we know that we have a good data set. So I could do a 45-minute presentation on this, so you're going to get a very quick snapshot today. So in the presentation, the slides you're going to see a lot of these types of pie charts, and half the pie chart you can see on the left-hand side is the perfluorocarboxylic acids, half the pie chart on the right side is the perfluorosulfonic acids, the yellow, oranges, and reds. A couple of precursors are included down here, the darker colors. Remember, these are the compounds that can break down and be transformed into these terminal perfluorocarboxylic acids and perfluorosulfonic acids. So this slide gives you a big picture summary of some of the different signatures that we can see, which can reflect different sources and even different fate and transport scenarios. So at the top of the slide here, you see an aqueous film forming foam, the firefighting foam source. You see more of the red and orange perfluorosulfonic acids. Towards the bottom here, you see more of like a plastic source maybe with more of the blue perfluorocarboxylic acids. So these types of signatures that we generate with the data can be used to identify various characteristics, and not just of sources, but also characteristics of different fate and transport scenarios, like the breakdown of telomers further downstream in a plume, and we can show a plume becoming more enriched in something else because of the breakdown of those precursors. And there can be changes in signatures also along a plume due to commingling of sources, causing differences in pie charts along the length of a plume. So one of the things we spoke about earlier was the analyte list. Nancy likes to call it the donuts. But what you analyze for will affect your forensics evaluation. So obviously, the more information we have on PFAS constituents, the better it's going to be for forensics evaluation. So this slide really just shows some of the common PFAS we've seen with different industries or products. You see the paper and food packaging industry, you see some side chain fluoropolymers, the N-ethyl perfluorooctane sulfonamidoacetic acid. This is a precursor. It's a breakdown of this other one here, N-ethyl perfluorooctane sulfonamide ethanol. You also see some of the shorter chain perfluorocarboxylic acids and perfluorosulfonic acids associated with the breakdown of this N-ethyl fossa. Textile and leather, we see polymers, PFOA and fluorotelomere alcohols, and the polymers could break down to PFOA and maybe some other perfluorocarboxylic acids. Mostly we would probably see perfluorocarboxylic acids though on these signatures. And the fluorotelomere alcohols, these are the more volatile PFAS. They don't really last that long, and they're typically identified as intermediates. So AFFF is obviously a super important one. It's a major source of PFAS contamination. We can differentiate different types of AFFF based on signatures. So whether it's the legacy PFOS-based AFFF, the long chain fluorotelomere, the 8,2 fluorotelomere sulfonate AFFF, or the shorter chain C6,2 fluorotelomere sulfonate AFFF. Wastewater treatment plants and landfills. This is a harder one because the common components of wastewater treatment plants and landfills are going to be very dependent on the sources feeding them. But 5,3 fluorotelomere carboxylic acid has been seen in a lot of landfill leachate, and there's papers out there stating it's a good marker compound for landfills due to carpeting. But we're actually finding that this particular compound shows up in the breakdown of other telomers too. That are not polymers, like 8,2 fluorotelomere sulfonate. So it's actually identified quite a bit, and I'm not really sure that it is any longer a great marker compound for landfills. And then metal plating, another one. This industry actually was allowed to use PFOS about 10 years longer after it was phased out in the United States before they went to the replacement fluorotelomere sulfonates. It's mostly used for chromium plating to prevent splattering of hexavalent chromium. And the F53B that's listed here, this is a replacement for PFOS as a mist suppressant. From what I can see, mainly used in China. But this particular replacement compound, interestingly, is now included on the EPA 537 analytical method list of compounds. So at TRC, we have done some work with forensics, and we've used PFAS forensics to assist in source identification. This slide shows you some of the different signatures we may see from different industries or different products. You can see on the top left here, we can differentiate different sources of AFFF. You can see a very unique signature down here for landfill leachate, and also a very unique signature from a plastics manufacturer. And also the signature here from a wastewater treatment effluent of a chromium plater. So again, these types of signatures can be used to identify various characteristics, and not just of sources, but different fate and transport scenarios. And the last slide I wanted to show you on forensics is about the analyte list and how important it is. So we know the standard PFAS analyte list is continuing to change. I do know one lab now that can report up to 75 different PFAS. But one of the problems is that the largest data set we currently have is from UCMR3. And that only includes 6 of the perfluoroalkyl acids. So the comparison of signatures, really requires careful consideration. And obviously we have to integrate this chemical data with hydrogeological data. It has to be a multiple lines of evidence approach. But this slide shows the exact same data set, but the evaluation looks really different based on the analytes selected. So you can see the pie charts on the left. If you look at the top and the bottom one circled, it looks like only PFOA. It could be a Teflon manufacturer, you might think, if you were looking at these. But if you look at the second set of pie charts on the right, these are the same 2 pie charts for the same samples, but with more analytes reported. And you can see something else is going on here, and these signatures are very different. So the analyte list is very important to think about if you are using the data for source identification. So that's just a quick preview, and that's the end of our presentation.
Great, yes. Hi, this is Jennifer again at NMOA, and we do have quite a few questions. That was a lot of information, and yes, some people that joined a little late. The presentation slides will be posted. Just takes a few days. I will be sending an email out to people when those slides are ready. So let's see. There's quite a few questions. Some of them are kind of going back in time here, but generally for the particulate that's in the samples and how the lab uses the particulate, which method is better, or when would you want them to do one thing versus the other with the particulate?
So I think it really depends on your data quality objective. So, when I talk to risk assessors, they want to know a total number, and that they would want the lab to include the particulates. If it's for compliance, you probably need to have a total number. If it's NIPTs, I think it's going to depend on how you're using the data. And we're trying to get more guidance on that too from even from regulators. I know there's a lot of regulators probably on this call. So if you have certain requirements in your states of what you think, because it's almost like looking at a total versus dissolved result. When you take out the particulates, you're not actually filtering, but you could be getting much different results.
And do you know from the lab which way they're doing it, or how do you find out what they're doing with it?
You have to ask. So I'm telling people now that this should be part of what they ask the lab when they subcontract with them, is how they're dealing with it, so ahead of time. And if you want to change that, if you want to talk to the lab about doing something different, you'll know.
You can also ask them, and this is part of the SAP procedure, when you're developing the SAP, you can ask them to handle it in a specific way, but you can also ask to see their SOP perhaps for preparation, and that might give you some insight into what they're doing, and then make adjustments to what your project needs.
Okay, another thought is over time, it seems like you should be using the same lab at the same site to make sure the same thing's happening with your samples, or what do you what can we do with the historical data and use it for understanding trends or anything? Like, it seems like there's so many potential problem variables that, I don't know, what can people do?
Well, first line of defense is to do a usability assessment of the historical data. Look at all the method blanks, the equipment blanks, the surrogates, whatever, and to judge whether there are data gaps or there's a bias in the data, and then knowing that you have specific potential differences in sampling and in how things were handled, take that into consideration when you're trying to compare data sets.
Okay. Has absorption of PFAS to the sampling apparatus been evaluated? So, whether it absorbs.
I'm not sure. I mean, I know that there's materials that are not recommended, like the glass and the low density polyethylene, because it's known to absorb PFAS more than high density polyethylene. I don't know of any other particular studies that were done on that.
But you could judge whether you're having that problem by doing your equipment blanks. You know, if you find that you're having a persistent issue with equipment blanks, then it could be that you're having absorption.
Right. Okay. How about analytical methods for other matrices like wastewater, like air? Do you know where we're at with getting some standardized methods for those?
Yeah, we keep hearing that it's coming this year.
It's spring.
Now air, there is a method out for air now. It's OTM 45 for source sampling, stack sampling. It's a draft method, but there are labs that are using it now. Okay,
method 537. But there's also 537.1. Is that using isotope dilution or not?
No, it's just a different, it's an update to 537. It's okay too. Again, those are drinking water methods. So, you know, there's not going to be many matrix interferences with drinking water. So it's probably okay. Isotope dilution is not in that method. But when you modify it for other matrices, you want to use isotope dilution.
Okay, for method blanks versus samples, does your 10 times rule scale with dilution for highly concentrated samples?
Yeah, I would say yes, typically it does.
Okay. Oh, someone was concerned, some sites have more than one type of contamination, so people might be out there focused on one different contaminant like petroleum and be sampling for that. So do they have to still take all the precautions? If there is also PFAS at the site, even when they're out there to sample not for PFAS, do they still need to take all the precautions because they're still, I guess, using the same wells and things? Yes, correct?
Yes, correct.
Okay. Let's see, I don't know this one, but can you attempt to explain the DoD new data qualifier X for PFAS data that fail a QA/QC requirement and how a project team should assess data usability? That makes sense to you?
Yeah. The X is DoD equivalent to using an R for reject. However, they leave it up to the project team to decide whether or not the non-detect should be rejected or not, depending on the project scope or the project objectives. Liz, do you have anything to add on that?
Well, actually, I just saw X used recently to mean that there's no secondary source standard available.
Ah, okay.
So I don't know. I'm not sure if I saw a lab utilize X and flag it as, you know, there was no secondary analytical source available. So they only calibrated, you know, with one source and couldn't do a second source standard. And when that happened, I still felt the data were usable.
Yeah.
But for some of these chemicals, I mean, there's not enough standards out there to even get second source. So
yeah, a big area for research is in obtaining more labeled compounds to be able to add to the extraction so that we can look at more broader compound list.
Right.
Okay, here's, maybe this is a wrap, that's a good wrap-up question. Let's see if I can get another one. Let's see, what time period did the modern fluorotelemers begin being used?
Oh, that's about the 19, I think it's towards the end of the 70s.
Yeah, that's what I was going to say too.
Yeah. But I think
Okay.
almost all manufacturers now that's what they're making. It's, they're not making the other kinds of AFFF anymore.
Right. Okay, well, it is 3 o'clock. I'm going to ask this last question, and I think I got to most of the other ones, but there were some more that came in. Okay, wait, here's one more. I'm going to ask one more and then the last question. What is your recommendation to regulators, since we have a lot of them on here, for use of biased high or low qualifier data for determination of potential screening values?
Could you repeat that question?
Well, yeah, I guess I wrote it a little wrong. What is your recommendation to regulators for the use of biased high or low qualifier data for determining the potentially whether they are there at screening values if you've got a bias?
Mm-hmm. I mean, I know typically what I would do is how close you are to that screening criteria. So if your data are biased low and you're still well below the screening criteria, I mean significantly low, then it's probably okay. If your data are biased low and you're just below the screening criteria, that might be more of an issue.
Yeah, this is another reason why you have to look at the cumulative effects
right.
on the data, so that, yeah, data that are estimated are absolutely usable for project decisions, but as Liz pointed out, depends on how near you might be an action level to decide whether or not you can use it.
Right, or whether you need to go and get another sample instead.
Or just look at the whole data set. Take a 30,000 foot view of the data, not on a sample by sample basis, but for the entire, a larger pool of samples and judge.
Right.
Well, I think with the regulators, a lot of times they're taking a drinking water sample from someone's home. So you kind of do have to go sample by sample. Okay, the last question, and because we're after 3, and thank you to everybody that joined, is there a good resource that this person's labeling usability assessments for dummies, but some plain English, understandable to the lay person, a resource? Has the ITRC worked on anything, or is any kind of?
So the next, actually, it might even be in the current ITRC PFAS document that's out there. We have created a table, and actually Nancy and I created it on data usability for PFAS, and we hope that it's helpful. And it's going through a couple more revisions right now that will be out in the next release of the document.
Great. So it's not quite available yet, but it will be soon.
It might. I think there's a version available right now, but ITRC is constantly updating this document, and we just made a few more revisions to it.
I would also point out that the NISDEC January 2021 document has a very nice section, a small section on data validation, which is a really nice tool.
Right.
Okay, and what was that again?
That's one of the references we've put up. Will be in the presentation. It's the New York State DEC sampling and analysis guidance for PFAS that was issued in January 2021.
Okay, so the New York State. And ITRC, I think it's itrcweb.org is their website, right?
I'm not sure, but if you Google ITRC PFAS, you will find it.
Yeah, okay. Great. Thank you so much. This is really important information, especially for regulators to be aware of. So I really appreciate Nancy and Liz's time today and their great presentation and this wonderful resource. So like I said, the slides will be posted, the PDF of them within the next week at the most, and I'll send an email out to everybody that attended. So with that, thanks again, Liz and Nancy, and I'm going to end the webinar for everybody and hope you enjoy the rest of your day. Bye-bye.
Thank you.
Bye, thank you.